Hey everybody! Today's lesson is on acid and base titration, something that a lot of high school grade 11 student will, I guess, have to do in order to, tell everybody that I have done grade 11 chemistry successfully. And what do I remember from it? Well, I did this really annoying experiment called acid and base titration. That's right. This is one annoying thing. Because if you were to make a mistake and put too much, oh man, you're gonna have to start all over again. So, what exactly is a acid and base titration? Okay, and now what equipment are involved? So let's take a look at the equipment part, letting you know exactly what the whole purpose of an acid and base titration is all about. So what I have here is a burette. Okay, that's this long thing right here. It's called burette. And what I have here is an aluminum flask. Now, some people may be doing this with a beaker, but I usually don't recommend a beaker. The reason is because if you want to mix this solution right here, you can just grab the skinny tip and just swirl. If you were to do that with a beaker, man, you're gonna make a mess, and not only you're gonna make a mess, but your result will be inaccurate if you have any some sort of spillage. Now the burette is scaled. Okay, they're scaled from 0 to usually 50 milliliters. Okay, and what's in here is a known concentration of what we call titrating. It could be an acid in there, or it could be a base, and all depends on what you're trying to find, because what goes in here is your unknown. So you have your unknown concentration, which you want to find out. Okay, so usually why we do an acid and base titration is that if we have some sort of unknown acid or unknown base, and I want to know what the concentration of this is. So you would perform a titration with a known opposite of what this is to do so. So let's say I have some sort of unknown acid in here. Okay, and that, well, not just, well, I know the acid, but I don't know the concentration of the acid. I should make that a little bit more clear. So, oh, that's out of battery. So if I have some sort of acid in here and I don't know the concentration, and I do want to know the concentration, I will titrate it against a base with a known concentration. Okay? On contrary, the same idea. Here, if I have an unknown base, I would put a known acid in here, so therefore I can find out exactly how it works. Now, how is the idea here? How does this really work? Well, the idea is actually very simple. It's all based on a neutralization reaction. So let's take a look at a neutralization reaction. Let's say you have HCl plus NaOH. This is a classic one that everybody knows. And a double displacement, or in this case neutralization, will give you water and NaCl. So let's say my unknown was HCl. Okay, let's say my unknown was HCl. Let's redraw this. Okay. Let's say I have HCl. Remember, in solution, HCl, being a strong acid, is fully dissociated. So that's what an HCl solution looked like in a flask. Now, if you have HCl here, obviously you will have NaOH in here. Okay, so we don't know the concentration of this, but we do know what the concentration of this. Let's just say the concentration of base that we're going to use is 0.5 molar. Okay, the concentration of acid obviously is something that I want to know. Now, first off, I need to know how much acid is in my aluminum flask. So that information is important. So let's say this is 10 milliliter. Okay? And my point of interest is this. I'm going to turn this valve open. Okay? When I turn this open, NaOH will start to, I guess, mix with the HCl. You might not want to open it fully, because if you open it fully, this thing would just gush out, and then you are going to miss what we call the endpoint. So usually I start this with a very gentle opening. That way you're dropping NaOH drop-wise into the aluminum flask full of HCl. Now, there's one more thing that you have to put into your aluminum flask, and that is called an indicator. In this case, we are working with acid and base. So what I want to do is I want to select an indicator where it tells me the endpoint, and I will tell you what the endpoint is all about soon, but yeah, you need to put an indicator here. And the indicator of choice is known as, it's called phenolphthalein. Now, phenolphthalein is, I guess you can call it a chemical that detects the presence of excess base. Okay? If your solution is basic, phenolphthalein will turn color from clear to pink. That's a very nice, hot pink, actually. A very beautiful color. So let's just say right now, this is all HCl. If you were to put phenolphthalein in here, you'll notice that there will be no color change. No, this is going to stay clear. But as you drop NaOH in there, phenolphthalein will detect, NaOH. But is it going to turn pink? Maybe just for a second. And when you mix this, it will go back to clear until you have an excess of NaOH in here. Okay? That's when phenolphthalein says, oh, you know what? I am detecting this OH. So let's take a look at how this works graphically. Okay, so I'm going to turn this on. So I'm going to let this stuff drip, 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 drip. So let's say I have 1 mole of NaOH dripped into my HCl. So let's take a look at what happens. So 1 mole. So I have 1 Na plus and 1 OH minus. What's going to happen? Well, this is going to happen. Water is going to be forming. Okay, now don't think the fact that NaCl is going to form. This is a solution after all. NaCl is soluble, so NaCl is really not going to come together theoretically. Okay, realistically, these guys are not going to come together to form a crystalline salt. It is going to stay as an ion, even though the equation says you're going to make NaCl, but really you're more like going to make Na plus and Cl minus, unless you evaporate this whole thing. Yeah, you may get your NaCl as a crystal, but in the meantime, Na stays as Na plus, Cl stays as Cl minus. But what you're going to get for sure is water. These guys are going to come together to form H2O. Okay, now, phenolphthalein. Is phenolphthalein gonna be detecting any excess OH? No. Maybe for a split second, once you drop this in there, it may say, ooh, I found some OH, let's turn pink. But as you swirl and mix, H will find OH to make water. Phenolphthalein will say, I'm turning myself back to clear. Hopefully you understand that. Let's drop another drop. Let's drop another mole here, NaOH. Okay, same idea here. OH will find an H, okay, to make another water. Again, phenolphthalein will detect the initial OH coming in, but after you do your mixing, phenolphthalein says, I didn't find anything because the OH that was in here hooked up with H. Okay, if you look at the solution right now, this is still an acidic solution. How do I know? Well, there's H's here. Okay, so I'm going to drop another drop of NaOH. There you go. I'm running out of room. Okay, Na plus, OH minus. Again, OH and H will come together to form water. Phenolphthalein is going to be pink, and then again, very quickly goes back to clear. All right? So you can see that the reaction has finished. Because take a look at this. Do you see any more acid in here? Do you see any more H+? The answer is no. All the H+ has hooked up with OH to form water. So theoretically, you are done. You are done. All you need to do is figure out how much titrant you just use. In this case, in the case of my drawing, you use 3 moles of it. Okay, but in reality, you're looking at a certain milliliter, you're looking at a certain volume. But you may be thinking to yourself, well, how do I know? If I were to do this for real, how do I know that this is the end? I have reacted all my acid with base. Well, you really don't. You really don't. But you know you're close. So what you want to do is you might want to jot down what this volume is, just in case something bad happened. Now, what do you mean by something bad happens? Well, let's just say you have shaky hands and you're trying to turn this valve to give one more drop into here. But you accidentally, turn it on too fully, and instead of one drop being in here, you have a few drops or a gush of titrant. Then you're gonna have to start this all over again. Man, how fun would that be? So this is the point where you're gonna have to be very careful, and you can sense that. The way to sense that is this. Remember what I said when you put a drop in here? Phenolphthalein will say, oh, let's turn pink because I see OH. And then when you swirl, it goes back to clear. When you're near, it stays pink a little longer before it turns back to clear. So let's say if the point earlier, before this happened, when you drop, when you put a drop of titrant in here, you'll notice it turns pink for a longer period of time. And when you shake and shake and shake, it took a while for it to go back to clear. That's when you know, oh, I'm close. So at this point, you might want to jot this number down, whatever volume you use here. Remember what I said, this stuff is actually to scale from 0 to 50. So you know exactly how much you used. All right, what happened if you make one more drop? What happened if you put one more drop of NaOH? Well, this is what you're going to get. NaOH. Check this out. OH will try to find his best friend H+ to form water with. Look at this OH that we just inserted into the LMR flash. Are there any H's to form best friends with? OH is like, oh, where's my best friend H? Earlier, my my other OH friends all found their partner. Where is my H? No H. Why? Because all the HCl, or H plus in this case, have been reacted. They got all been reacted. OH will be now an excess. Who will take note of this? Phenolphthalein will take note of this. Phenolphthalein will say, hey, OH, how you doing? Are you alone? What happened? You can't find an H to form water with? Well, guess what? I'm going to turn this solution pink. Oh, this is more purplish. That's not pink. Let me try that again. I think it's more like this. Yeah, this is the color. I'm going to turn the solution pink. This is when you know that, it's done. You're done. Okay. That one drop, that final drop, that turned the whole solution pink because of an excess of OH, indicates to you that titration is done successfully, and you should read out exactly how much titrant you use. Now, you may be thinking to yourself, didn't you use kind of too much? Yes, you did. You actually used one drop too much. Usually, one drop is around like 0.5 milliliter. Okay? I guess what you can do is subtract what you use by 0.5 milliliter. Or, I think just by writing in what you use is pretty much good enough. So let's write that. Okay, let's just have some sort of imaginary. Let's just make up a number. The amount of titrant used, let's say, was 5 milliliter. Okay, let's say you drop 5 milliliters of this into here to make it pink permanently. Okay, all right. Now, if you look at this right here, this is really just an ordinary, stoichiometry question. Solution stoichiometry question. You're asked to find what this unknown is. Given the fact that you know what you're titrating it with the amount of volume used, you know exactly how much volume of HCl you started with, you can easily find out what this is. And let's do that. All right. So, stoichiometry. Let's go. 0.5 moles per liter of NaOH is what inside your burette. And guess what? You use 5 milliliter. I was going to say millimeter. Okay, so 5 milliliter was used, okay, to completely react with whatever acid that was in here. So there you go. Okay, you're left with mole of NaOH. And we all know that for every mole of NaOH is equivalent to a mole of HCl. Okay, so mole can go, NaOH can go, and what is the mole of HCl in this case using stoichiometry? Well, it would be 0.0025 mole. Okay, now to finish off, concentration is equal to mole divided by volume. So what you have here is 0.0025 mole, and you're going to divide that by the amount of HCl that was in your Alamar flask. So in this case, it will be 0.01 liter. Okay, so your unknown concentration of acid was actually 0.25 molarity. Okay, so the acid has this concentration. Okay, so I would say it's a very powerful tool used to find unknown concentration of substances, but it is definitely a way to do this. And it can be very annoying because, as I said, if you overshot, okay, if you put too much of this number would have been bigger. If this number is too big, obviously it will affect the unknown concentration of what that really is. Okay? A very, very popular high school experiment that pretty much every grade 11 student would do. Anyway, hopefully you understand how this works. I have a couple of questions that I'm going to work out with you just to make sure that you guys are, experts in this. All right. Now, what if I have the other way around? Okay, somebody might want to know, what if I have, something else? So let's clear this. And let's clear this. Okay? It's actually not difficult. So let's say I have this. Okay? Let's say here my unknown was NaOH. Okay? And my known is HCl. Okay? So we flip the two chemicals. Now, would it be different? No, the idea is actually pretty much the same. The only difference is when you're doing this is that this will start out pink. Okay, because once you drop the phenolphthalein in here, it will note the fact that, oh, your unknown is NaOH, it is basic, there's a whole bunch of OH in here, so this is going to be pink. Okay, so as I release HCl in here, okay, OH will find H plus to turn water, and until this is all gone. So your what we call endpoint will go from pink to clear. Okay, rather than what we saw before, where we went from clear to pink. Again, that last drop that turned this clear is your final endpoint. And if you want to be super precise, you can subtract 0.5 milliliters out of it. Okay, but usually people don't do that. People just take the final drop that turns this completely pink or turns this completely clear as their endpoint, because that 0.5 milliliter is really not that significant. Okay. All right. So I'm hoping that you understand the theory behind what titration is all about. So let's take a look at a couple of questions. Okay, I have a very nice question right here. Okay, example 1. I don't mind drawing this for you. So here's your burette. Okay, here's your Alamar flask. It says you have 25 milliliter of hydrochloric acid in here. Okay, you are titrating this with a standard 1.25 molar solution of barium hydroxide. Okay, and it tells you right here that you are going to use 45.2 milliliters of this barium hydroxide to completely react with 25 milliliter of HCl. My question is, what is this concentration? Okay. So I already have the reaction here for you, and it's already balanced. The balanced part is actually very important. And let's put in some of the numbers in here. So again, I don't know what this is, and that is obviously my mode of interest. I know that in my flask, there's 25 milliliter. This is actually a very, very important number, okay, because you need to divide the mole of HCl later with this number right here. So you're going to have to make sure that is correctly in here. And one of the more correct way, or most most accurate way of inserting a liquid, of course, is the use of a pipette. Okay, so barium hydroxide. Okay, so 1.25 in molarity and 45.2 milliliter. Okay. All right. Hey, you can just do your stoichiometry and figure out exactly what the unknown is. After you put in all these numbers and understand exactly what you need to do, I'm going to do this a little differently. I know in the previous example, I changed all my milliliters to liters. I mean, do you have to do that? No, you actually don't have to do that. Because remember, this is really a ratio of moles per liter. So if it's moles per liter, it could easily be millimoles per milliliter. That's exactly what I'm going to do because I don't want to convert this to liters. It really doesn't matter. Your choice. All right. So here it is. Okay. Let's do the stoichiometry. So 1.25, let's just call this millimole per milliliter. Instead of moles per liter, it's really the same thing of BaOH2. And I know for a fact that I'm going to use 45.2 milliliters of it. All right. So here we go. Milliliters and milliliters cancel. So for every mole, or in this case, millimole of BaOH2, it is 2 millimole of HCl. Okay, millimole and millimole cancel. BaOH2 and BaOH2 cancel. So let's take a look at what this is. It will be 103 millimole of HCl. Okay. Let's find out the concentration. So 113 millimole divided by 25 milliliter. Okay, that will give me an answer of 4.52 molar. All right, so pretty simple, pretty simple. I mean, simple on paper, but if you're actually doing this, it's actually quite frustrating. So a lot of times, people would do it twice, maybe 3 times. You know, the first time is always like a rough trial. That way you kind of expect where the endpoint is near, so you be careful around that area. But yeah, some people, I mean, some people can do it once and, you know, be very accurate about it because they're very careful. I'm not. All right, let's do another one. Okay, so in this question, let's draw this. Here's my burette. Here's my flask. Okay, so you have 0.025 liters of sodium hydroxide. So you have sodium hydroxide in here, and it is 0.025 liters. Obviously, the concentration is something that I'm interested in, right? And I'm going to titrate this with 0.5 molar of nitric acid. Okay, and I'm going to use 15.6 milliliters of it to reach endpoint. To go from pink to clear. Notice I said pink to clear, not clear to pink, because this is started off as a base and you're adding acid to it. You know, phenolphthalein will sense that, ooh, this is going to be pink. Okay, and as I add this, it will, I guess, be less pink until it is completely clear. Hey, another stoichiometry question. Let's go, let's go. So again, I don't know the concentration here, but I do know that I'm using this as a volume. Okay, 25 milliliter or 0.025 liters. Here, 0.5 molar at 15.6 milliliter. Okay, be careful of units. Make sure, of course, the units are consistent. So if you want, you can make this like the other questions, millimole, or you can just change these milliliters to liters. Let's do the latter, okay? So let's go. This is going to be 0.0156 liters. No big deal. All right, let's do the stoichiometry. I like this. This is 1-to-1, so therefore it makes the calculation much easier. So 0.5 moles per liter of HNO3 and you have, or you use 15.6 milliliters of it to reach endpoint. Okay, and for every mole of HNO3, it is equivalent to 1 mole of NaOH. So 0.5 times 0.0156, or 0.0156 divided by 2, is 0.0078 mole. Okay, let's scratch out these guys. And concentration will be 0.0078 mole over 0.025 liters. That will give me my concentration to be 0.312 m. So my unknown NaOH concentration was 0.3. All right. Hopefully that this is something that you can easily understand and is not giving you much of a problem. I mean, like, the math-wise is never a problem. It is when you're actually doing this that makes you very frustrating. It frustrates me all the time. All right, let's call it. I'm sure you guys get the point. Bye now.